Welcome back. This is lecture number 32. In this lecture, we are going to talk about impedance analysis and stability. So, in this lecture, we are going to recapitulate our practical voltage source model, which we discussed in lecture number 13. Then we want to again demonstrate the supply disturbance under pulsating load, and then we want to identify the need for input filter. Then we want to discuss the Middlebrook extra element theorem for impedance analysis with input filter, and then impedance analysis and stability criteria for switch mode power converter with input filter. So, practical voltage source driving a practical DC-DC buck converter, this thing we have discussed in lecture number 13, and we have identified a practical voltage source should have output impedance which will consist of one DC term, which we generally consider in any practical voltage source like internal resistance or a series resistance, but we in a practical voltage source should also have a frequency dependent term, because none of the power supply have infinite output impedance, infinite bandwidth. Okay. So, this we have discussed in lecture 13, okay, and it is driving a practical synchronous buck converter. We have also developed model, and we have discussed in lecture 13, this model was developed. So, practical source, we also consider, we build a Simulink model, and we have also discussed about the dynamics in the block diagram of the Simulink, and we have taken this parasitic for the input filter. That means, it has a inductor 20 nanohenry, then it has a filter capacitor which is 100 microfarad I took here, then RF1 is the DCR of the filter capacitor and RF2 is the ESR of the filter capacitor. Sorry, RF1 is the DCR of the filter inductor and RF2 is the ESR of the filter capacitor. And we have also shown this MATLAB simulation case study. What did you do? So, we consider a buck converter where this input voltage was actually a practical voltage source. That was a practical voltage source. And here we are comparing, sorry, this is a voltage source model, I am sorry, this represents a voltage source model. So, this is an ideal voltage source. So, this is an ideal voltage source, and this Vs is the this is the actual output of a practical voltage source. So, we are considering an ideal voltage source with its output impedance. Now, this result we have discussed in lecture 13, where if we draw pulsating current like a step current from this source, where red color is the step current, suddenly we are drawing 10 ampere current at some point, then this blue trace indicate the source voltage with practical output impedance. There will be effect because it does not have infinite bandwidth, but the red one which we consider when we consider an ideal voltage source. So, there is a subtle difference between ideal and practical different voltage source, not only in terms of their DC, but in terms of transient behavior. And we also discussed the different shift in the output voltage for a practical source is due to the DC value of the output resistance or output impedance. That means, this is the output resistance, there will be a drop, and that we consider any practical voltage source in our undergraduate course. We have been taught with this, right? We are familiar. Now, the practical voltage source driving a practical buck converter, we know the input current of a buck converter is discontinuous. So, earlier we considered a pulsating current externally by putting a current source and turning on and off. But now, when you connect such source to a DC-DC converter, since there is a switch and this switch turns on and off, so the input current of the buck converter is discontinuous. So, it will appear like a load step transient for the source, and that will happen twice in a switching period, because once it will turn on and then it turn off. So, it will have both undershoot overshoot effect for each transition of the switch of this switch, and that will impact the supply voltage. If the supply is really very well regulated, very high bandwidth or maybe a very large capacitor, then it will try to hold it, right. Otherwise, most of the power supply now presently we are getting are basically SMPS type. Earlier power supply which was quite bulky, okay, they are based on the linear transformer, right, that means a 50 hertz transformer. But now most of the power supply are coming with high frequency transformer, switch mode power converter, because we need to reduce the size of the supply, make it lightweight. So, where I mean those supply require very tight control in order to regulate the output voltage and nullify or reduce the transient effect. So, that but still since the input current is discontinuous, so in most of the cases we should not connect a buck converter directly to a source, because the discontinuous current can inject some kind of transient effect in the output of the source, and that will inject, and that input discontinuous input current is the cause of conducted EMI. So, there will be some amount of power with this transient frequency, that higher frequency, and that will interfere with the communication devices. So, generally we need to put an input filter in between the source and the converter, so that the source will not see this discontinuous current. Okay. So, you need to filter out. So, input filter, now this is a standard buck converter where this is a practical voltage source that we have already modeled earlier source, and in order to avoid the disturbance in the source, we are putting an input filter here. When you introduce an input, so please consider this Z out is the output impedance of the filter, because we have put all impedance of the source inside this block only, because otherwise it will be too bulky. That means eventually we have, as if in the modeling sense, we have an ideal voltage source, source output impedance, input filter, then DC-DC converter. Okay. But here we are talking about the Z out is the output, is the impedance of the input filter, okay, while it is driving a buck converter. So, without input filter, we have derived the control to output transfer function for a duty ratio control. What was that? We got V0 tilde by D tilde, and this we obtained from where? We obtained from our equivalent circuit model. Okay. But now all these derivations was carried out considering there was no input, there was no the practical source. I mean, it was an ideal source, it was not a practical source, but in reality it is a practical source, and we need to put a filter. When you put a filter, then this control to output transfer function will be affected by adding this input filter, and this modified transfer function, control to output transfer function, we do not need to rederive, and that fundamental work was proposed by Middlebrook using extra element theorem. That means that transfer function can be updated while considering another output impedance by using extra element theorem, and that can be derived using this method very effectively. So, that means this is that control to output transfer function with filter, it is with input filter, and this is the control to output transfer function without input filter. That means with filter will be without filter multiplied by this term. What of this term? Z out, this one is nothing but, this Z out is nothing but the output impedance, this is already there of the input filter. That means this you know, you don't need to write. Okay. So, this you already know, this is the output impedance of the input filter. But what is Zn? This is a control to output transfer function without filter. Zd is the input impedance of the converter while considering open loop. That means there is no duty ratio perturbation. That means as if we are running the converter with fixed duty ratio and we are injecting, that means this is the input current to the converter and we are measuring the impedance from looking from this side of this converter. So, that impedance will be the input impedance of the converter when we operate in open loop. So, this is done. Then what about ZD? Sorry, that is ZD. What is Zn? Zn is the input impedance of the converter when we have forced the output voltage to be perturbation to be 0. That means, we need to make a control in such a way whenever we inject this current, we will not see any effect in the output voltage. That means, output voltage should not be affected by this. It means that if we inject a sinusoidal, that means if we inject a okay. So, if we inject a AC excitation, that means if we apply an AC excitation, I am talking about the AC model from this side, this is my AC excitation I have given and this is my input current of this converter. Now, it will see an impedance Z in, where we have a closed loop control and we will control the tightly regulate the converter in such a way that the perturbation or the frequency excitation in the input will not be reflected in the output. That means, output will be insensitive to the input voltage supply rejection, that means input voltage perturbation. So, this transfer function is called Zn. That means, we need to have a suitable control mechanism by which we can actually nullify this effect. And how can it do that? We can do that even using feed forward control also, that we have discussed, right. So, that means, we need to place a suitable control logic to do that. We can use a simple voltage mode control with an input voltage feed forward, and if we do that, then you can reject the disturbance in the output side. That is our objective. And if you do such control technique and excite, whatever impedance you will measure, that will be Zn. How to find out Zn? First of all, input impedance of a buck converter, we already have an equivalent circuit model and we know how to derive it, right. But in the first case, if the converter is in open loop, then this term will go away, right. That means, it will be shorted, no output current perturbation. Okay. So, it will look like this, it is shorted, no output current, and we can derive Zd, that is the input impedance of the buck converter under open loop condition, and this is a standard input impedance expression of a buck converter under open loop. This is well known. In fact, at very low frequency, you will see the whole impedance, if you go to come to very low frequency, if you substitute S equal to 0, that means your Zin 0 will eventually become R by D square. Okay. And this is particularly input impedance low frequency behavior. It is important when we consider a converter while it is connected to a PV load, solar load, we need some impedance matching. Okay. But solar is a very slow process, and so even though we have an input impedance frequency dependent term, but while connecting to solar we can take low frequency behavior which will behave like a resistive load. Okay. Now, so we can find out this input impedance for open loop, and this we have already derived. But what will be the input impedance of a tightly regulated buck converter? Because we told you that means if we inject an AC excitation in the input, we must nullify that in the output in order to get this transfer function, and that we can do one way by using voltage mode control with input voltage feed forward, even if we can do current mode control also, but we want to make sure the voltage is controlled. Then if we control it, then the right hand side of this there is no perturbation. So, that means if you go back to the circuit, if there is no perturbation in the output voltage, if the voltage perturbation is 0, which means the current perturbation to the resistance is 0. Okay. Similarly, the current perturbation to this capacitor must be 0, otherwise any perturbation in this you will have an impedance of this, so it will be reflected, which means the current perturbation of this also has to be 0. That means our inductor current perturbation will also become 0 in this case. I am not talking about this case, I am talking about the next case. So, this whole model will appear, but it does not mean that it will be a short circuit, because it is still drawing current, because voltage is tightly regulated. In that case, it will appear like a like constant power, right, because your power is constant for a given resistive load, output voltage is constant, and this is exactly what we do. So, this constant power is nothing but because the voltage is regulated at its nominal value, and what is the power? It is V0 nominal square by R, because R is the actual load resistance. So, we can force to 0, then Zn can be identified. Now, if we take this constant power load, that means it is a DC characteristic, right. So, in order to find this, how to start with? So, it will behave like a output voltage is tightly regulated, it will behave like a constant power load, and power magnitude can be obtained V nominal square by R, and in a DC-DC converter under ideal condition D into V in, so you will get this expression. Next, in constant power load, since this product of V in into I in, I will say it is not the perturb term, because it is the actual term. Perturb term is 0, but I am saying that if you take actual input voltage into actual input current, they are basically constant. That means, if you take DC, this is anyway constant. If you take DC plus excitation, power is constant. So, under that case, if you draw current and voltage, they will look like a rectangular hyperbolic curve, right, because their product is constant. And if you take at operating point, because this is the point where this is our nominal input current and this is our nominal input voltage, this is my operating point, and if you take the slope of this curve, this will this will give us the incremental change, that means delta, I can say delta V in by delta I in. So, this is the incremental change that we can expect, this will be the slope, okay, and we need to find out what is this, okay. So, we need to find out this. So, we need to find out what is this. In order to find out, we know the product is constant, and if you take the partial derivative, it is the Zn. Now, what is Vin? We know that Vin into Iin is nothing but our P0, right. So, if you take substitute, P0 is nothing but, we already discussed, D into V in whole square by R, and this can be written as V in into In, because we are assuming it is lossless converter for the time being. So, input power and output power are same. From here we can find out what is my V in by I in. So, you can see I can cut this with this one. So, I can take this side. So, V in by I in will be simply R by D square. Now, if you substitute here, so you will get Zn is equal to minus R by D square. This is exactly what we got, right. So, Zn equal to minus R by D square. Okay. So, that means input impedance of an ideal buck converter, there are two type of impedance. One is for the null condition output voltage, that is the tightly regulated, another is the traditional input impedance with open loop converter. Okay. Then effect of input control to output transformation ideal buck converter, we have we know about we applied the Middlebrook extra element theorem, and we can write it down. The converter with filter and this is without filter, we know the transfer function of the ideal buck converter. So, we can actually write down, we can take it here and we can analyze. So, you can write down this. So, what is the criteria? ZD, all this we have derived. Stability criteria, the stability requirement, the magnitude of the output impedance of the input filter should be much smaller than the magnitude of the null input impedance. Similarly, the magnitude of the output impedance should be smaller than the input impedance of the DC-DC converter. That means, this will make sure that their effect is insignificant. But this does not say anything about the phase response. This is an amplitude response. It may so happen within the control bandwidth, that means there can be multiple crossover frequency, and this multiple crossover frequency, if we can ensure this criteria, the system will remain stable with input filter and without input filter, both are stable, because without input filter you have designed the converter, it was stable. With input filter, if we ensure this, it will be stable, but multiple crossover frequency may lead to poor phase margin. So, you may get some oscillatory behavior. That means, we need to talk about the transient performance. So, for transient performance, we need to match the crossover frequency with input filter and without input filter. In essence, we want to achieve, that means, if we can get GVD like this, then with input filter you may get some peaking effect here, but it should actually otherwise match. So, if this will not cause any extra crossover frequency, and if you ensure that your crossover frequency remains unaffected with and without input filter, and phase margin at this point remains same and no additional grand crossover frequency, then you can say with and without input filter the performance will be closely equivalent. So, that means one is stability criteria, that means with input filter we want to make sure the converter is stable, but this is not sufficient because it will impact the transient performance. In fact, we saw even the source impedance, the input, the behavior of the converter was different. It was really, we will take this in the design case study later, but we want to make sure that the cutoff frequency is not affected and phase margin is not affected, then we can maintain the similar transient performance. So, in order to stabilize the converter, we need to put a damping to the input filter, because if you take an ideal LC filter, this will be oscillatory and it will definitely make, it will make the system closed loop unstable. So, in order to damp, one way to put a resistance in series parallel with the filter capacitor, another you can put a resistance in parallel with the inductor, but both the technique it will be lossy, and there are a lot of research that happen thereafter, but for more details, but stability requirement, the filter resistance for both of these cases must be smaller than, much smaller than R by d square, which is the magnitude of the Zn. It is nothing but R by d square. In fact, if you take Zd magnitude at omega equal to 0, it will also be same, R by d square. So, this must be smaller. For other approach, please refer to fundamentals of power electronics book, and also you can refer to more research paper. So, with this I want to summarize the modeling of ideal and practical voltage source aspect were discussed, output impedance of input filter were discussed, then impedance and stability criteria of the switch mode power converter with input filters are also discussed. So, with this I want to finish it here. Thank you very much.